Hi, I'm Fabian Reiter, and in this video I'm going to talk about a paper I've recently presented at PODCI 2024. The paper is called A Local View of the Polynomial Hierarchy. But what I'm really going to do is tell you a little story about reverse engineering a theory. You see, proving theorems is quite difficult, and sometimes I like to take a backwards approach where I first state a theorem I would like to be true, and only afterwards come up with the matching definitions that actually do make it true. Now, this might not sound like a very serious way of doing research, but I promise there will be a point to the story. In this particular case, I was inspired by Fagin's theorem. And this basically says that there are two equivalent ways of defining the complexity class NP. On the one hand, there's the classical definition based on Turing machines, and on the other hand, there's a more obscure definition that uses logical formulas. And what Fagin's theorem says is that we can effectively translate between these two. Now I thought it would be rather nice to somehow extend this to the setting of distributed computing, so that instead of a single Turing machine, we could talk about a network of machines. And to put this differently, my explicit goal was to extend Fagin's theorem to the local model of distributed computing. So let's start with a quick recap of the local model. Basically, we've got a network of machines that all run the same algorithm. Each has a unique identifier and possibly some local input, and they communicate via synchronous message passing. And more specifically, I'm interested in distributed decision, where the nodes communicate only for a constant number of rounds and then have to collectively decide whether their network satisfies some graph property. If all the nodes say yes, the graph is accepted, but if at least one node says no, the graph is rejected. For instance, this allows us to easily check if the graph is Eulerian. Each node simply says yes if and only if its degree is even. And here in this graph, since there are two nodes of odd degree, they say no and the graph is rejected. Now, by itself, this model is rather weak. So to make things a bit more interesting, we introduce Eve. She can have a look at the entire graph and then assign some certificates to the nodes. This allows us, for instance, to check if the graph is three-colorable. First, we let Eve choose a three-coloring, and then we let the nodes check that their own color is different from their neighbor's colors. Since this is the case here, the graph is accepted. Obviously, the underlying assumption here is that Eve wants the graph to be accepted. So as long as there exists a valid coloring, she will find it. Now, to make things even more interesting, we introduce a second protagonist who will play the role of the opponent. This is Adam, and he wants the graph to get rejected. And now we let the two play a game. First, Eve chooses the colors of nodes of degree 1. Then Adam chooses the colors of nodes of degree 2. And finally, Eve is supposed to choose the colors of all the remaining nodes such that the entire graph is well colored. But this is not possible here, because Adam was clever. And no matter what Eve tries to do, there will always be at least two adjacent nodes that share the same color. And so, the graph is rejected. This means that although this particular graph is three-colorable, it is not three-round three-colorable because Adam has a winning strategy. However, if we take the same graph and just remove a single edge, then things become much more difficult for Adam. Again, Eve chooses the colors of nodes of degree 1, then Adam chooses the colors of nodes of degree 2, but this time, no matter what Adam tries to do, there will always be enough free colors for Eve to win the game. And so the graph is accepted. This means that this particular graph is both three-colorable and three-round three-colorable because Eve has a winning strategy. And more generally speaking, we can consider games with an arbitrary number of alternations between Eve and Adam, and then try to classify graph properties according to the type of game that characterizes them. For instance, three-round three-colorability is what we call a sigma 3 property because it's characterized by a three-round game in which Eve starts. And similarly, classical three-colorability is a sigma 1 property because it's characterized by a single-round game in which only Eve plays. And of course, we can also consider games in which Adam starts instead of Eve, and for those we will use the letter pi instead of sigma. Now perhaps you have already seen this framework before. In fact, there have been at least 3 papers on the very same topic. So, what's different this time? Well, remember that my goal was to extend Fagin's theorem. And although I did not really explain what this means, the point is this pushed me into a new direction. First of all the previous papers make the standard assumption that nodes have globally unique identifiers. But in order to get Fagin's theorem, I had to assume that identifiers are only locally unique. By this I mean that if 2 nodes are sufficiently far apart from each other, then they may share the same identifier. Second, all the previous papers assume that certificate sizes may depend on n, the total number of nodes in the graph. Now in the examples we just saw, certificates were always colors, so their size was constant. But in general they could be arbitrary strings whose length depends on n. However, in order to prove Fagin's theorem, I had to assume that certificate sizes depend on the amount of information that nodes can see locally. And more specifically, I had to assume that the size of a certificate given to node V is polynomial in the size of V's constant radius neighborhood. And third, all the previous papers assume that the node's local computation time is either unbounded or dependent on n. But again, Fagin's theorem imposes polynomial bounds with respect to constant radius neighborhoods. So basically, the main difference with previous work is an even stronger focus on locality. And this was not a conscious choice, but rather a direct consequence of my attempt to reverse engineer Fagin's theorem. But now one can ask, what's the point of having Fagin's theorem anyway? Well, as I said, this theorem basically lets us translate between logical formulas and Turing machines. And now imagine we have some questions about the local model, and suppose we are okay with the restrictions to locally unique identifiers and local polynomial bounds. Then using Fagin's theorem, we can take these questions and translate them to the world of logic to see if someone else has already done the hard work for us. So in some sense, Fagin's theorem connects the local model to an entire body of literature that seems to have nothing to do with distributed computing. For instance, there are some major results on monadic second-order logic on grids, and also some classical results on finite automata and their connection to logic. Now, it's not really important to understand what these results mean by themselves, because what I'm going to focus on is their implications on the local model. So, what can logic tell us about distributed decision? To explain this, I first have to define some complexity classes. Let's start with LP, which stands for local polynomial time. This is just a class of graph properties that can be decided without any certificates, so without any help from Eve and Adam. Building on that, we get sigma 1, which corresponds to single round games with only Eve, and similarly pi 1, which corresponds to single round games with only Adam. And then by letting the 2 players alternate, we can build an entire hierarchy of complexity classes on top of that. Now this sounds very similar to the classical polynomial hierarchy, and in fact this is even a direct generalization of that hierarchy. You see, each of these classes talks about networks of nodes, but if we restrict networks to consist of a single node, then we get the corresponding classes of the classical polynomial hierarchy. So in particular, the class P is just LP restricted to single node networks, and similarly NP is just sigma 1 restricted to single node networks. However, in the case of arbitrary networks, the problem of separating these complexity classes becomes easier. It's still not trivial, but thanks to Fagin's theorem, we can capitalize on the work of smart people in the logic community to show that all the inclusions shown with red lines here are in fact strict inclusions. So the hierarchy is provably infinite. And for the remaining inclusions shown with dashed lines, the question of strictness remains very difficult because these are in fact equalities if and only if p equals np. This also means that from the point of view of distributed computing, the really interesting classes are those highlighted in yellow, because the remaining classes are basically just artifacts of this particular definition. So what's inside the yellow classes? Let's look at some examples of graph properties. In LP, we have Eulerianness, which is actually a representative property for that class because it is LP complete under an extended form of polynomial time reductions. Then, one level higher, we have three-colorability, which is again representative for that class because it's sigma 1 complete. And by the way, this can be shown via Fagin's theorem. And probably much higher in the hierarchy, we have Hamiltonicity, which is both LP hard and co-LP hard. Here I don't know exactly where it lies in the hierarchy, but I have an upper bound of sigma 5 and a lower bound of sigma 1. And finally, Fagin's theorem also allows us to show that some properties lie completely outside the hierarchy. And an example of such a property would be that the number of nodes in the graph is a prime number. Alright, but at this point you might be thinking, well, that's a nice little story you're telling here, but why should we care? I mean, the local model was basically defined to study the notion of locality. But here I'm making statements about some hybrid setting that uses the local model but then mixes it with some notions from classical complexity theory. So it's not clear at all whether this makes any meaningful statement from the point of view of distributed computing. In fact, the results would be much more interesting if we could at least get rid of the polynomial bounds. So let's do that. Here's a hierarchy very similar to the previous one, but this time we replace polynomial bounds with arbitrary bounds. By this I mean that identifiers are still locally unique and certificate sizes still depend on constant radius neighborhoods, but this time the dependency is not necessarily a polynomial but can be an arbitrary computable function. So what can we say about this generalized setting? Well, quite conveniently, all the separation results from the previous slide carry over directly to this setting. So again, we get an infinite hierarchy. But this time, for the remaining inclusions shown with dashed lines, we get honest equalities that do not depend on P versus NP. And this allows us to clean up the picture because we only have to keep the yellow classes, and so we're left with a linear order of complexity classes. And on top of that, if we slightly adapt the notion of reduction, then all the hardness and completeness results from the previous setting also carry over to this one. So this leaves us with an infinite hierarchy of complexity classes, and at least in principle, these can be interpreted as a measure of locality. On the lowest level, we have purely local properties because by definition, they depend only on the information that nodes can see locally. But the higher we go in this hierarchy, the more global information can be either proved or disproved by even Adam. The main point that remains unclear to me for now is how meaningful each of these levels really is. And probably the best strategy to get a feeling for that is to look at many more examples of graph properties and try to place them somewhere on the scale. Anyway, I'm afraid this story has a rather tragic ending. Because although we can generalize most of the results from the previous setting, there's one thing that gets lost. And that's Fagin's theorem. So that's quite ironic, isn't it? This was the starting point of the entire story. It guided the definition of the framework, and it was the main tool used to prove most of the results I just presented. And yet, it's the only thing that does not generalize. Let me conclude this talk with an analogy. Here's a picture I found on the website of a Swiss railway company. This was taken over 100 years ago, but I guess at the time the photographer was not aware of one particular thing. They were taking a picture of Fagin's theorem. Can you see it? It's right there. It's this wooden structure upon which you can build a theory, and once you're done, you just remove the structure, but the theory remains standing. Thanks for listening.